Okay, so just to review steady state pump data. So the main point in this lecture is to cover pumps, basically how pumps and valves cause transients and how they are modeled in Hammer. So when we're talking about pumps, we have a rated head for each flow, and the pumps usually should stay within that operating range. You usually specify a pump definition that may or may not extend all the way out to zero head and zero flow, but when you're talking about a transient simulation, it's very important to make sure that the pump is operating close to its best efficiency point. It's certainly within its operating range, but it's that much more important when you're dealing with a transient simulation that the pump is operating near the best efficiency point for reasons that I'll get into in a little bit, but it basically has an assumption built in that it is operating near its best efficiency point, and that's to do with how it constructs a four-quadrant pump curve based on the initial operating point. You'll also, when you're dealing with transients, you'll want to check your net positive suction head, NPSH, to avoid cavitation problems. So that's sort of a general note on, on pumps and what you want to watch out for. As far as where you get the information on pumps, usually you get that from the manufacturer. There's usually some catalogs available even for older pumps, and usually they're tested in a factory, so that the data is usually pretty good. Now, obviously, if the pump is older and it may not be performing as it was when it was first installed, you might have to do some on-site testing with some meters, to make sure that you're properly representing the pump, because if you don't do that and you assume that it's using data from a catalog, then you may be modeling something that's not really the way it's going to operate in the field. So here's a typical steady state pump curve. You'll see that this is operating in what's called the first quadrant, so positive head, positive flow in this case. And towards the left side, when you're dealing with all the way down to zero flow, that's called your shutoff head. So your maximum head at zero flow, and the way off to the right sometimes is referred to as the run out. So this is basically your maximum flow with a zero head added. And then the dashed line here is your efficiency curve. So as you're operating somewhere on the red line, the pump curve, you have a certain efficiency associated with that, and usually your best efficiency point is somewhere near the middle. But when you're dealing with some complicated pump curves, it may not, you may not be able to assume that it's right within the middle. So Hammer, as well as WaterCAD and WaterGems, allow you to plot both the pump definition head versus flow curve, as well as the efficiency curve in the same axis, and that way you can see, if it's operating like where this gray dashed line is, then you'll know exactly what the operating point is and the efficiency point. So again, is it really performing as rated? So what you want to do is avoid using incomplete or wrong data. So, even though you may enter the manufacturer pump characteristics, and even if it's a new pump, the pump may not necessarily be operating exactly as expected. So some things that influence this include trimming of the pump, wear and tear just over time, cavitation damage on the pump impeller, and possibly any nearby bottlenecks that you might have. So during the transient simulation, the operating point may change, even if the pump is not shutting down. So even if it's operating at a constant speed and you're not modeling that particular pump shutting down, it may shift on its operating point. So in the transient calculation options, you can specify the pump as a report point, and that way you can actually view the time history data on the graph, as we did yesterday in the workshop, where you were able to graph things like flow and vapor volume. So what you can do is add the endpoint of the pipe next to the pump, and I recommend either side of the pump, both sides, and that way you can graph things like flow and pressure and head on the suction and the discharge point. You'll also notice, and I'll switch over to Hammer in a moment, and this is related to the right side of this slide here. There's a tab called Extended Node Data, and for a pump it shows extra information that's specific to that exact node. So rather than the time histories, which is showing you some result at the end of the pipe next to the node, when you're dealing with certain element types like pumps and hydropneumatic tanks and turbines, and there's a couple of others, there's an extended node data tab that allows you to graph specific things right at that node. So for a pump, for instance, speed. So I'm going to switch over to hammer for a moment here to show you. In the properties of a pump, you can see that there's a field down here called report point. I don't know if you can see that clearly, but it's under the transient reporting section. And when you enter a number in this field, that will tell the program to save those kinds of extended results at every, for instance, if I say 10, that means it's saving those results at every 10 time steps. If I want it to save at every single time step, I would enter 1 for that. But usually you don't need to see those kind of results for every single time step, so usually you enter something larger than 1 to reduce the amount of time it takes to run. But as we saw in the slide, which I'll switch back to, at the bottom right, once you've entered a number in the report period and computed the model, you will see that element available in the drop-down there for node, and you can graph those things like speed for a pump. And that way you can see exactly how the pump speed is changing over time, in addition to looking at the head and flow next to it. So different types of pumps and specific speed. So for hammer, it considers a pump to be a rotating equipment, basically. So you've got a motor, a shaft, transmission, and an impeller. They're all rotating. So it's characterized numerically by an input field called the specific speed. And that's something that you enter in the Transient tab of the pump definition. So it's an optional piece of information for initial conditions and WaterCAD and WaterGems, but for hammer it's required because that's how the pump is actually numerically simulated. So different types of impellers, there's lots of different types. You've got your centrifugal pumps, which are the most common, vertical turbine, multi-stage, reciprocal pumps, positive displacement. So that your centrifugal pumps and your multi-stage pumps, those are simulated as the regular pump node. But when you're talking about some of the other types of pumps, which we'll touch on a little bit later, like positive displacement, those don't really act the same way as the other pump types, so you need to model them a little bit differently. So talking about specific speed here, here's the equation for estimating what that specific speed is. So specific speed is a number like 1280, and there's units associated with it, sometimes denoted by an NS. So this is the equation you would use to estimate it. So it is accounting for the rated flow and rated head and rated speed. So when we say rated, we're talking about the values that are pretty close to the best efficiency point. So something that is sort of the normal operating conditions. And that's part of the reason why I mentioned earlier that it's very important to make sure that your pump is not operating in a strange, an abnormal place on its curve, because the results may be skewed because of the way that the specific speed is using it. So the reason why it needs to use the specific speed is because when you're dealing with a transient event, the pump may not be operating in the positive head, positive flow, everything being positive quadrant. You're actually dealing with a four-quadrant pump definition. You think of it almost as a circle, where you might be operating in the negative head, negative flow, and hammer really needs to be able to accurately simulate what happens in those conditions. So for that reason, we estimate the specific speed, we assign that to the pump, and then the pump takes the rated flow, rated head, and rated speed from the initial conditions, your starting initial conditions, and it constructs a four-quadrant curve based on the shape that's defined for that specific speed. So hammer has a collection of default specific speeds that you can pick from, and we'll see that in a moment. And when you pick that, it's basically telling the program to use a certain shape for that four-quadrant curve. So it applies that shape. It's like a dimensionless curve that it's applying to your initial conditions, flow, head, and speed to construct the representation of how hammer will treat that pump when it needs to operate in those other quadrants. Inertia is another important thing for pumps, so that is also entered in the transient tab of the pump definition. And at the bottom of the screen there's a little screenshot of a tool that's included in there for estimating that inertia. And that's very important because when you're saying that a pump is shutting down, you're not saying that the impeller is suddenly, going from whatever it was to zero. You're saying that the electrical supply, the electrical torque, is suddenly stopped. So there's no longer any torque applied to that impeller, but the impeller itself may still take some time to spin down, and that's based on the inertia. So it's very important, especially for a shut after time delay pump event, that you enter the appropriate inertia, because that will definitely affect the transient response to that type of shutdown event. So simple pumps in hammer. So there's two different, and there's a little screenshot at the bottom that shows you the different types of transient pumps that can be represented in hammer, and that's a little drop down in the pump properties. If you have a pump that isn't shutting down, isn't starting up, isn't moving during the transient simulation as far as the speed or the torque, then you have two different constant speed options. So you may wonder what the difference is between those. So the constant speed no curve means that it does not change its speed, but it also means that it will use the four-quadrant curve from the specific speed that you choose. So it is possible that that pump could operate in the other quadrants just based on whatever else is changing, the hydraulics that are changing elsewhere in the system. So even though you may have a constant speed assumption there is a possibility that it could operate in negative flow, negative head. It may need to use those other quadrants. Whereas the constant speed pump curve designation means that it doesn't change speed, but it's limited to that first quadrant operation. So the reason why we have this is so that you have an ability to say that you want to force that pump to use the exact pump definition, the head versus flow curve, that you entered in the pump definition, rather than using a four-quadrant curve where, because of that shape that you're applying it to, it may not necessarily follow exactly on that curve that you entered in the pump definition. So the effect of speed or impeller change. So this is sort of showing you how a pump curve scales up and down as you're changing the speed, and the impact of that, which some of you are probably familiar with. Now there's affinity laws that you're also probably familiar with that estimate the head and flow as you change the speed, and that's used in hammer. Now a different impeller will also change the torque, and the motor controller also changes the speed or the torque. So in hammer you can either enter a speed or a torque versus time, a pattern, if you're changing either of those two over time. So you have the ability to say, I want to directly control how the speed changes over time, or I want to directly change how the applied torque changes over time. And that's very important. One of the articles that I linked to covers that, but basically if you're saying that you want to, for example, model a pump shutdown followed by a pump startup, well, normally you have the ability to just say shut after time delay as the transient pump type, and that basically simulates the applied torque dropping to zero at the time delay that you choose. But if you were trying to use the variable speed option, as you can see in the screenshot at the bottom there, this is actually the reverse. So I'll use that example. So the bottom there shows a pump start. So when you're modeling a pump startup event, you have to specify a pattern that defines basically how quickly or slowly the pump is starting up. But you have to choose between speed or torque, and you can see the control variable is set to speed. So when we're saying speed, that pattern is directly controlling the speed. So you might be tempted to just say, just have that pattern instantly go up to 1.0, meaning, a zero speed to full speed. But that's not really what happens. It takes some time for that pump impeller to spin up. So you either need to control it by speed and assess and implement, that the actual delay that it would take for that impeller to actually reach full speed, implement that into the pattern there, or choose the control variable as torque, and that way you can say instantly 0 to 1 within a fraction of a second, and that's like flipping the switch. So instantly you're applying torque to the pump impeller, and then the rate at which it increases up to full speed or even beyond is up to the inertia. So it's something to keep in mind. It's a very important concept. If you don't realize those assumptions, you could potentially set up your pump event incorrectly. Some advanced stuff. So these are some of the other different types. I've already touched on this a little bit. Shut after time delay. So you're entering all those things we just talked about, and you're entering a time delay, like 5 seconds, which means 5 seconds into the simulation, the electrical torque applied is dropped to 0. You also have an input for a time to close. So you have the flexibility to say that in addition to shutting down, you might have a check valve built into it, or maybe you have a control valve that closes at some point between the start of the simulation and whatever time that you enter. You'll see this pump here is set as shut after time delay, and I've entered 5 seconds as the time delay. And it's recommended that you do that as opposed to a 0, because that allows you to see the results in those first 5 seconds and confirm that there's nothing happening that shouldn't have been happening, which is sometimes referred to as an initial surge or a spurious surge. So if there's some problem with the setup of the model and a transient event is basically being induced when you didn't expect there to be, then if you introduce that 5-second or 10-second or whatever delay, then you can observe the transient results in the first 5 seconds and make sure that nothing is happening. You want to confirm that things are steady, and then have the shutdown occur. So pump valve type is what I was just saying, that you have the flexibility to choose between a check valve and a control valve. So you might wonder, well, what if I have neither? What if I don't have a check valve or a control valve? So currently the way that you model that is you would choose control valve, and you would just enter a very long time delay, something like that, which basically means it's not doing anything. But typically you would likely have a check valve. Maybe you want to be conservative and assume that the check valve isn't going to work, or maybe you don't have one, or maybe you want to model that check valve explicitly as the check valve node element. So it gives you the flexibility there. So variable speed and pump start are pretty much the same. In both cases, you're specifying a pattern of how that pump changes over time, as I was saying. And there are some articles, again, in that additional resources module on the right side that go into a little bit more detail of the different types of pump events. So system head curves and total dynamic head, this is probably a review for you guys, but there is the concept of the system head curve when you're dealing with pumps. So the point at which the pump is operating is where its pump definition, its head versus flow curve, intersects with the system head curve. So the system head curve basically defines the downstream system and how it reacts to different flows. So depending on the flow that's entering that system, you have a different amount of head that would need to be added to overcome that. So that's how it finds the operating point and the initial conditions. So some points to make here is that you definitely will want to include any minor losses that you may have in the pump station to make sure that you're getting an accurate system head curve, and therefore your initial operating point of your pump is correct. And the rest of the slide just goes into the different types of profiles that you may have and the different components. So you have a static lift, which is basically the difference if you're dealing with pumping from one boundary condition to another, like one tank to another. You have the static head, which is just the difference in the hydraulic grade of those two boundary conditions, and usually that's uphill, but sometimes may actually be downhill if your dynamic losses, your friction losses, are high enough. So there's two components to the system head curve and the head that the pump is adding, and that's actually defined in this next slide here. So you can kind of see visually, this dark black curved line on the left side is your total dynamic head. So you have a component of, so this is another example here. So the two orange boxes are two different tanks. So you'll see the downstream tank is at a higher hydraulic grade. So the majority of the head that the pump has to add is a static lift. So that's this portion right here. The dynamic lift is basically the head loss. So the loss from friction going from suction tank to receiving tank. So there's two different components there. So suction, piping, and station losses, again, it's important to include those, as they could be significant. So suction system limitations, this can sometimes occur if you have an older pump station with a sort of smaller diameter suction pipe, and then you maybe upgrade the pump station, but you don't upgrade the pipes. So you might have a bottleneck, so to speak, on the suction side of your pump because of that undersized piping. So something you'll definitely want to check in that case is the net positive suction head. As you know, if that drops too low, you can have problems with local cavitation, like the videos that I had mentioned yesterday. So without suction limitations, you can basically connect all the pumps to a single tank or reservoir and not have to worry about that. Discharge losses. So some limitations there. You would want to check if pumps were upgraded, but existing piping was kept, kind of like what I just said before for the suction side. So if you upgrade the pump and you did not upsize the piping, then you could have a bottleneck there. Again, cavitation can be an issue if there's excessive losses. You can also have a check valve slam occur if you have a check valve built in there. Especially if there's a nearby storage tank. So like if you have a hydropneumatic tank just downstream, there's a very good chance that that check valve is going to slam when that pump shuts down. So that's definitely a concern as far as the discharge system. If you're ever in doubt, model it in the program and calibrate the discharge system to measurements that you've taken in the field. Okay, so that's pumps. When it comes to check valves are another component that you need to consider. They can impact a transient response both positively and negatively. If you have a check valve that is closing too quickly, that can cause an upsurge event, a water hammer event. Obviously check valves prevent backflow. You have to specify a downstream pipe designation on your check valve element, so you're directing, which direction the flow is allowed to pass through. There are a couple of different ways to model check valves. So in this slide, we're showing you the different ways. So the first one is to actually explicitly model it as the check valve node element. And that's the most complex way to do that, because you're able to actually enter an open time and a close time. So the time it actually takes between when it senses reverse flow and when it actually closes, and vice versa, and also a threshold pressure to reopen. So sometimes you need some amount of pressure to actually reopen a closed check valve. So you can have some interesting behavior here, because if you assume an instant closure like you would with a pipe check valve, as you can see in the second example, or even the pump check valve, those are assuming an instant closure. So that could actually not be conservative, because the water column is essentially at rest at that instant that it first starts reversing. So typically you would get the most conservative results if you actually introduce that time delay that it takes to close, especially to close that check valve, because in that time between when it first starts to reverse flow and when the actual valve is closed, you've built up some reverse velocity. So the water column has started to accelerate and move in reverse, and if you're then stopping it, then you're stopping a greater momentum, and that can result in a greater transient event, as we mentioned in the first session.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.